Okay, so the next question was about gravitational fields. It's question 9 on the HL and I think question 7 on the SL. And so the first question was asking you to define gravitational field strength. Okay, so remember the equation G is equal to F over M, so the gravitational field strength is equal to force divided by mass. So my definition for it is the force per unit mass. We always have to say on a small positive test mass. Okay, so giving that equation up there. Okay, so that was 1 mark for that. The next one was then asking for the SI unit of gravitational field strength. So if it's force divided by mass, okay, it's newtons per kilogram. Now we know that G can also be meters per second squared, but that's when we're talking about G as being acceleration due to gravity. But this is specifically about the field strength. So the field strength unit is this one, not the acceleration unit. Okay, so being really careful with that bit there. Part B was asking then a little bit about circular motion, and we had the planets orbit the sun in a circular motion with the orbital time period of t and an orbital radius r. The mass of the sun is m. Okay, so we need to show that t is equal to this little equation up here. So in this case, remembering that gravitational field strength can be equal to the acceleration. So again, I'm looking at the acceleration in terms of like circular motion up here. So I'm going to be saying that gm over r squared is equal to v squared over r. Okay, so in terms of like circular motion acceleration, we give it by this equation. All right, so if I resolve this, I can therefore say that V is equal to GM divided by R, and that little bit there showing that sort of equating up here gets you 1 mark. We also know that speed is equal to distance divided by time. So for a circle, okay, the distance it's going to go is the circumference, of a circle, so that's 2 pi r, divided by the time period, which would be the orbital period of t in this case. So again, what I can now do here is I can sub in for v squared. So v squared was equal to gm over r, but it's also equal to 4 pi squared r squared divided by t squared. Okay, so I'm essentially squaring this up here. Now this r up here, okay, will actually resolve and come up there. Okay, if I'm trying to kind of put this, sorry, that's my cat jumping off. Come up here to become r cubed. Okay, and then I can switch my t squared and my gm, so t squared is equal to 4 pi squared r cubed over gm, and then to work out t, I just need to square root. Okay, so in this case, it's 4 pi squared r cubed divided by gm. The next bit then was asking then to estimate the mass of the sun. Okay, so I essentially want to use this equation up here. So I've been given lots of different things. I've been given the radius of the orbit, so I can sub that in. I want to find out the m, pi I know, g I know, and t I can find out. So the orbit of the Earth around the sun, it takes 365 days. There are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So there's 3.15 times 10 to the 7 seconds in 1 year. Okay, simply then rearrange this equation. So m is equal to 4 pi squared r cubed over g t squared. So I've simply just rearranged this equation to put m as my subject. And then simply plugged in my value, so 4 pi squared, 1.5 times 10 to the 11 cubed, over g, so 6.67 times 10 to the minus 11, and then t, which is 3.15 times 10 to the 7 squared, so that equals 2 times 10 to the 30 kilograms, which is very, very massive.